All right, so it says a child sits at the edge of a 4 meter long teeter totter that has a pivot at its middle. So, teeter totter is just a 4 meter long plank. There's a pivot at its middle. And I have one child here, 50 kilograms. All right. This is 2 meters. An 80 kilogram friend sits on the other end. If they start at rest with the teeter-totter perfectly horizontal, what will be the instantaneous angular acceleration of the teeter-totter the moment the two children lift their feet? I see 4 forces acting in this system. There's the force from this child. There's the force from this child. There's the weight of the plank itself. And then there's, the normal force from the pivot, whatever the mount is. Net force is not 0. I know this is a homework question, but as we discuss some of these problems, there are things that are nuanced portions of the problem that might not be asked here, but are certainly fair game. The center of mass of this system is going to accelerate downwards. I'll say that again. The center of mass of this system is going to accelerate downwards. There is absolutely no reason that you couldn't be asked, what is the acceleration of the center of mass of the system? It's a net force problem. And the forces are unbalanced. There are 3 downward forces. This force will not be as great as the sum of these 3 forces. And that's because this kid is accelerating downwards while this kid is accelerating upwards. More mass is going downwards than is going upwards. So the center of mass of the system is accelerating downwards. Now, the actual torque problem here, since we have a fixed pivot point, net torque equals I alpha. You asked, so what direction do you want to make positive? Into the board or out of the board? Out of the board is positive. All right. So I have the torque from the 80 kilogram boy and the torque from the 50 kilogram boy. Let's see, torque arm length is 2 meters for the 80 kilogram boy. The size of the force, 800 newtons. And I would argue that they gave me all the information to set sine at 90 degrees. 50 kilogram boy is also 2 meters. Their force is 500 newtons, and again, sine of 90 degrees. Using the right-hand rule, it looks like this kid's into the board, and that kid is out of the board. So we'll make him out of the board and him into the board. That is my net torque. So it looks like negative 1,600 plus 1,000 equals I alpha. I think that's all I need from the torque portion of the problem. So let's do this portion of the problem. I need the moment of inertia of the system. The moment of inertia of the system appears to be 2 point masses and a rod rotated about its center. So 1/12 mL squared for the teeter-totter and 50 times 2 squared for one boy and 80 times 2 squared for the other boy. This has to be the moment of inertia of the system. Any question about where any of that came from? All right, so I cancel one of the 3's with the 12, that's 1/4. So this has got to be just 40. Somebody check my math on this. 2 squared is 4, that's 200. This is 320. Is that all good? So 560 kilograms meters squared. So negative 600 equals 560 alpha. So alpha's got to be negative 600 divided by 560. I don't know what that is, but that's got to be our answer. 1 point something. So, not terrible. The problem goes on, but the next part of the problem is largely similar. They do ask us to find the linear acceleration of both children. They are both on the ends of the teeter-totters, so their linear acceleration has to be the same because they're both the same distance away. So that's going to be, the negative here doesn't mean as much. The negative tells us that the system is going to rotate this way, right? That's what the negative is telling us, the direction of the rotation. So this boy will accelerate downwards at the same rate as this boy will accelerate upwards. And that's just going to be alpha times r. So r is 2, so 2.2 meters per second squared, and 2.2 meters per second squared. The problem changes in the next part. The bigger kid moves towards the center to try and see if they could equal it out. Do you want me to do the second version of this problem too? Okay. So again, we just move the guy in, add up our new moments of inertia, change our torque, and again, I think this comes out to be 0.625, but you should check my math. I'm pulling this from memory. So again, I'm going to try and figure out what the accelerations are. This guy is going to be 2 times 0.625, or 1.25 meters per second squared. And this guy is going to be 0.625 times 1, so his acceleration is 0.625 meters per second squared. All right. We're trying to find the center of mass of the water molecule first. This is going to involve quite a bit of trig and some geometry. I want to find a location. So I think we could all agree that the center of mass has to lie along this line because of the symmetry of the water molecule. Is that all good? Okay. So I can consider that there is a mass here along this line that is 2 AMUs, and this one is 16 AMUs. Right, along this line, in this dimension, these are the 2 hydrogens as they would be if we looked at this as a one-dimensional problem. Does that make sense? We're going to, of course, need this distance in order to do the center of mass formula for point masses, but we have that. This entire, well, we don't have it. We have the stuff to find it. Isn't this whole angle 104.5? So that makes this angle 52.25 degrees. Is that right? Yeah. And this is 95.7 picometers. Pico is 10 to the negative 12th, but I'm just going to leave it in terms of picometers for the whole problem. So this side from here to here, that's just going to be based on the sine. I'm going to need you guys to help me out with this, but I'll call this based on the cosine. So the adjacent side there is 95.7 cosine 52.5. Okay. So this distance is 58.59 picometers. All right, so center of mass formula is in one dimension because we're treating it along that line. So I guess y would be better. I don't know. Just need a variable. Y center of mass equals the sum of MIYI divided by the total mass. So I'm going to choose the center of the water as my, as 0. So that means the mass of the water is 16, and the distance from my reference point to the water molecule is 0. And then I go to the next mass, which is here. That point mass has a mass of 2, and it is located 58.59 away from the reference point, all divided by 18. So this will give me my Y center of mass. I have the solution sitting in here somewhere, but I think it's better if you guys have some hand in this, so. What you got there? 3.25. I thought it was 6. 6? Okay. So picometers. Yeah, I got 6 when I did it, 6 something. So I have a lot written here, and it might be distracting, but keep in mind that's like, based on how long this is, it's like really close to the water molecule, but not quite. So this is going to be our center of mass. So to calculate the moment of inertia, we treat that as our location, and we have to find R for each of the masses that is part of our water molecule. So there's going to have to be a R here to get to the center of the water molecule, and there'll have to be a R here to get to that hydrogen molecule, and another R here to get to that hydrogen molecule. Now, probably the right way to do this would be law of cosines. I didn't. I was not feeling like looking it up, and I hate the law of cosines. So I found this distance next. And this is the opposite side, and it is just 95.7 sine 52.5. Could somebody work that for me? 76? All right. So this is 76. Because I'll tell you what I'm trying to do. I'm trying to figure out the length of this side. I need to know that length. I already have this length, but I don't have this length. So if I get this number, I know that this length from here to here is 58.59 minus 6.51. And so I can find the hypotenuse of, let me see, can I draw a triangle right? Nope. I can find the hypotenuse of that triangle. You guys see what I'm trying to do? Yes, no? So to find the hypotenuse, it's going to be, let's see, 76 squared plus 58.59 minus 6.51 squared, all to the 1/2 power. And this comes out to be like just a little bit less than 95.7. But I don't remember how much less. Yeah?
To get the distance where the center of mass was, whether you subtract 6.51 from 58.59.
I'm trying to figure out this distance right here. Oops, not a triangle. Let's see. I'm trying to figure out this distance to use for that triangle. 58.59 is this distance. And 6.51 is this distance. Okay. So what do we get for our new value? What's H? 92. All right, so now we have all the pieces we need. Super tedious, I know. But here we go. I'm going to slide this over to the side and leave just enough. My moment of inertia is for 3-point masses. One of them is the mass of hydrogen, 1 AMU, times its distance away from the center of mass, 92. There are 2 oxygens, and so they are equidistant away. It doesn't matter that one's in one direction or one's in the other. They contribute the same amount to the moment of inertia. Then I have the moment of inertia of the oxygen molecule, although much bigger, 16 AMUs. It is located 6.51 picometers away from the axis of rotation. That's your answer, whatever that is. It's like 17,000 AMU picometer squared or something like that. It's something stupid. If you're asking, would this be on the exam? No. Would you have to calculate a 2-dimensional point mass? Yeah, sure. They just wouldn't make you do all this trig ahead of time. And if you did it with the oxygen in the center, you get a slightly larger value because the hydrogens actually contribute the most to this because they're so far away. Sulfur dioxide, which looks a lot like a water molecule, won't oscillate in a microwave. Its moment of inertia is different. And so you can't heat it up using a microwave. The only thing that heats up in a microwave is the water. And the water transfers its energy to the rest of the food. All right, fun. We're going to do this as a lab in a couple days. On the board yesterday, I did indicate that there was a possibility of extra credit if you were, and by extra credit, I want to be careful. I have just not enough equipment. It's just toilet paper. So if you wish to participate in the lab, having rolls of toilet paper would be helpful. I could see my way clear probably to unlock a locked assignment or maybe add a point or 2 on a test if you were to bring a roll of toilet paper with your name scrawled on the outside like this. That way as it unrolls, I still know who turned it in. All right, so this is the problem that we have here. And it says a very long ribbon is rolled until it makes a solid disc of radius r and mass m. The end of the ribbon is held in place, and the ribbon is allowed to unroll as it falls, as shown above. All right, so it's going to roll. So we talked about rolling yesterday. What is the acceleration of the ribbon as it unrolls? So I think they want the linear acceleration of the ribbon. Looking at this problem, I see a unbalanced force and probably an unbalanced torque. So I'm going to assume the net force on the toilet paper is equal to MA. I think there are 2 forces acting on the toilet paper. I think there is a gravitational force that's acting straight down from its center. And I think there is a tension acting on the edge here. And because it accelerates downwards, I don't think those 2 are equal. I think they're unbalanced. This is where I would start the problem, like any force problem. Anything weird about that? So we're good to go? All right, since I did that part, you draft for me a net force equation. Have some stake in this. I could just do the whole thing, but you're about to have to do something in a minute all on your own. So should I call on one of you for this? Be fun. It's not hard. So who should I can't pick on Viv. She's not supposed to be here, so you're not here. And if I pick on Bao, she'll say, no, don't pick on me. I wasn't here yesterday, but we didn't do this yesterday. So it would be just fine. We did this in November. So that seems like a fair thing. What would you do, Bao?
I don't know.
Really? Well, it says net force, so I need you to add up forces. Which force is this one?
Mass.
Mass isn't a force.
Oh.
Weight, sure, mg, great. And what's this one? Tension, excellent, excellent. How might I mash those together to show the whole world that I am adding together all the forces? We could do it that way and that'd be fine, except what direction do you think the toilet paper's gonna, or the roll of ribbon's gonna go? Do you think that it's gonna accelerate downwards, or do you think it's gonna accelerate upwards? I think so too. Let's make downwards positive then. Excellent. mg minus t equals ma. Perfect. It's a net force equation. So I don't know t, so I don't think I can figure out the acceleration from here. I'm getting the idea from just looking at this. I'm allowed to use m and r and fundamental constants in my answer. T can't be in the answer, so I need another way of figuring out t. Is it likely that the toilet paper roll is going to spin? Oh, I keep saying that because that's the lab. Is it likely that the ribbon is going to spin on its way down? All right, so the only way that can happen is if there's an unbalanced torque acting on the system. So net torque equals I alpha. With torque, you have to choose a pivot point or have one chosen for you. Where would you like the pivot point to be? There's two places to choose, and one of them would be the center. That's actually not where it's pivoting, but we could work the problem this way. It's actually pivoting here because this point is not moving with respect to the system. It pivots there, but then it unrolls a little bit and the pivot point changes. That's what we talked about with rolling yesterday, that a thing that's rolling has a single point that's not moving for an instant, and then it rolls a little more and then it goes to the next point that's not moving for an instant. And it continues doing that. So I don't care which of these we use. For this problem, we can use either. So you said center, so we'll do center. But the truth is, you should see both. So it doesn't take long to do both versions. Okay, so we're gonna do the center first, and then we'll do the edge. I would strongly encourage you to take detailed notes here on the steps of what you have to do, or else your notes are useless. So the first thing was, do you think it's going to accelerate? We said yes. Do you think it's gonna rotationally accelerate? You said yes. This is a series of steps. The next thing I suggested you do, outside of the force problem, was to make decisions about direction. We made downwards positive. I think it probably wouldn't be a bad idea to make this direction the rotational equivalent of positive. So out of the board is positive for our rotational direction. Then you had to choose a pivot point. It's probably not in your notes, but you said you don't know where to start. I'm telling you where to start. Now, this says to add up the torques and set it equal to I alpha. We're gonna probably have to do a few things here to make that happen. I remember that torque is R dot F dot the sine of an angle. So if we're gonna use mg as our pivot point, then I think R is probably that, because the tension is being applied at the edge of the ribbon. So I'll make that our torque arm length. And our force is T, and that looks like a right angle to me. So I think it's R times T times the sine of 90 degrees. And that's the only torque because the weight is acting at the pivot point, and that's a torque arm length of 0. So this is it. This is our only torque. I'm going to set that equal to I alpha, but this is a disk. So I know things about its moment of inertia. You have a table there, but I hope you start to memorize a few of these. A disk has a moment of inertia of 1/2 mr squared. All right, we have done the net torque portion of the problem. We've identified a torque relationship that might be able to help us solve the problem. Except now we should be faced with another question, one that you should have in your notes. If we want to bring these two things together, I recognize that I have 1, 2, 3 different unknowns, T, A, and alpha. So it's time to ask, is the linear acceleration of this ribbon roll related to the angular acceleration of the ribbon roll? And I think the conditions for rolling are met in this problem. So A equals alpha times R. We've talked about this for the last 2 days. I'm going to sub in for alpha because I indicated to you guys that generally if you sub in for alpha, you tend to have the R's cancel out. So that's what I'm going to do. It seems clear to me that the R's will cancel out. I don't know that it seems clear to you. I've looked at your math, and sometimes you don't math as good as I think you should. But I'll do this in 2 steps because somebody showed me their paper yesterday, and I was sad. I'll cancel this R with that R. And now I'll cancel this R with this R. Are you now convinced? That person's in the room, they should be convinced. Substitution. Or just add these together and get mg equals 1/2 ma plus ma. I'm pretty sure that's 3/2 ma, right? So 3/2 ma mg. I'm going to cancel the m's since there's one on each side and solve for a, and a equals 2/3 g. What is the acceleration of the ribbon as it unrolls? It is 2/3 g. All right. I said we should do this both ways, and I stand by that. So I don't want to do it the other way for you. I want you to do it. So I'm going to call on one of you. And I probably am feeling vindictive right now. So I'm going to call on somebody who has brought me sadness in the last couple of days. And that's a handful of you people. So hurry. This is your pivot point. Again, we have the torque. It's RMG. But you can't use the center of mass as your moment of inertia. You have to shift it. I wrote it there. Andrew, what'd you get for the moment of inertia? I just kind of think of you as the any man. Oh, way to come in a clutch. Your friend help you out there?
I mean, I showed him my notes and it was on my notes.
All right. It's not much. It is 3/2 mr squared. Does anybody need me to explain it?
Yes.
1/2 mr squared plus mr squared. When you add those together, guess what you get, Leah? 3/2 mr squared. You're shifting it a distance r. And yes, we did this in class already. So 3/2 mr squared times alpha. Any questions? Oh, just like before, this is the right angle. So I'd say we replace alpha with a, and we get RMG equals 3/2 mr squared a over r. And I hope you see that you're going to get the exact same answer. You have to. The m's cancel out, all the r's cancel out, and a has got to be 2/3 g. The question goes on to ask you, what is the tension? Well, what we have written here wouldn't tell us the tension, but because we have the acceleration, we could probably figure out the tension some other way, like right here. That'd probably be the best place to find the tension. So tension equals 1/2 m. A is now 2/3 g. Whenever you have a problem that does not have numbers standing for mass and such, leave everything in terms of g. Don't put a 10 in. So 2's cancel and I get 1/3 mg. All good? If instead you want the disc to stay in place, how much tension would you have to apply to the ribbon? That's a terribly easy question. Who knows it? Go ahead. mg. Yeah, if I want the disc to stay in place, I need to make sure the net force is 0. Done. Oh, wait, D. What acceleration would you have to give the end of the ribbon? Well, that's a good question. I like that one. Try it. You know what the tension is. You know what the size of the inertia is. Pick your favorite thing here and find alpha or find A. If you don't know where to start, I'll tell you where to start. You have two forces that act on this object. Pick a pivot point and go. All right. How many of you did the problem about the center of mass of the toilet paper? None of you? So all of you did it over on the other side, over here? None of you? Oh, that's not good for you. We're almost at quiz time. So pick one of those. I mean, I know which one I'm going to pick. Let me correct my mistake before anybody notices. Nobody noticed my mistake. Nobody. There. Corrected my mistake. It is just RMG. I chose the center as my pivot point. The center of mass is staying in place. So I think it made most sense to make the center my pivot point. Although you might think this one is rolling, you could still use the other side, but it's easier to use this one. You won't know which one is easier to use. But that means that the torque is me pulling on it with tension, and the tension is mg because the net force is 0. So this is my unbalanced torque. It's a disc, so I put in a moment of inertia of a disc. And then I wanted the acceleration of the ribbon. So I put in A so that I could get it in meters per second squared. And it looks like if I want the ribbon to stay in place, I have to accelerate the end of the ribbon upwards with an acceleration of 2 times g to get the ribbon to stay in place. I want you to imagine an arrangement where I have some round object. Doesn't matter whether it's a hoop, a disc, a ball, whatever. It's going to roll down a ramp. Friction is required for the object to roll down the ramp. If there's no friction, the object slides down the ramp because there's no external torque there to make it turn. I want you to think for just a minute, if we have a coefficient of friction of 0, then at this point, there can be no frictional force in either direction. And although the weight of the object is acting straight downwards, none of the forces acting on the system can cause a torque because there's no point about which there'll be a pivot. I mean, truthfully, there's only 2 forces under these circumstances. A normal force upwards that's acting through the center of mass, it can't cause a torque. And the weight could cause a torque if there was a way for this point to be held in place. But with no point there to hold it in place, it won't stay in place. There'll be no torque and the object just slides. So for an object to roll down a ramp, there has to be an unbalanced torque, and that's going to require, in this case, some frictional force there. Now, if it's kinetic friction, like say you've broken static friction and it's kinetic friction, then there's not going to be a connection directly between the linear acceleration of the object and the angular acceleration of the object. But if we want it to roll, then there needs to be enough static friction for this point to stay at rest relative to the surface. Now, with all that being said, the amount of friction actually required and the direction of friction are things to be thoughtful about. It's not always what you might think it is. If the object is going to start from rest, I think we can all agree that for it to roll, there has to be a frictional force in this direction. There's several reasons why you should be thoughtful about the direction of the frictional force. I'm going to put you in some situations in a bit where it's not going to be as obvious. But the thing you should consider is, if this is going to roll down the ramp, what direction would it spin? It would have to spin this direction for it to roll down the ramp. And the only way it can spin that direction is if there's an external torque acting on the object that would cause that directional spin. Well, if the pivot point is at the center, clearly the friction would have to be this way for that to happen. Or even if we consider the pivot point to be here, then the weight is causing definitely a rotation in that direction. We could choose either point to be our pivot point to analyze this, but I want you to note that deciding the direction of the frictional force should be one of the first things you do when you encounter a problem that involves rolling and a ramp. If it's a force problem. If it's an energy problem, perhaps not. What I would like to do is I would like for you to see how you would solve for the size of this frictional force. The reason is you can't solve for it directly in the methods that we've used in the past, meaning we can't use friction is less than or equal to mu times the normal force. We're not going to be anywhere near the threshold for this. In order to determine the frictional force for something that's rolling, you're going to have to do the problem where the frictional force is the unknown and you're not subbing it for something else. So we're not going to use this at all. What we're going to do instead is we're going to use the forces and the knowledge that this point right here is instantaneously at rest on the surface when the object is rolling. Now you have a choice to make before we get started. The first choice is whether we make the pivot point the point of contact or the pivot point the center of the sphere. Neither one provides us with a benefit. We just need to start generating some relationships. So which would you like to do this problem? Would you like to do the problem with the pivot point at the surface or at the center? Sounded 50-50 to me. So we'll do center. I know that feels like that's the most reasonable thing to do. Surface is actually where the pivot point is. The only reason we can treat it at the center is because the center is a non-inertial reference frame, and you're allowed to be in any non-inertial reference. I'm sorry, the center is an inertial reference frame, and you're allowed to be in any inertial reference frame. So let's label our forces: normal, mg, and friction, and we're using the pivot point here at the center. Our net force equation is pretty straightforward because we've done this before. I'm going to set my coordinate system to be aligned with the ramp. So I'll make that y and that x. So the net force in the x direction will equal ma. And that's going to be mg sine theta minus friction equals ma. This is still an object moving down a ramp, and forces don't change just because it's rolling. So the way you deal with your forces is still going to be the same. So you guys tell me what the net force in the y direction must be. Must be 0, and what will this equation look like? What?
Mg cosine theta minus normal force.
All right, mg cosine theta. I'd probably make this the -1 and make the normal force positive, but it makes no difference. All right, so we've handled the force problem. Obviously, since we can't use this, there's no way to determine the size of the frictional force from this because we don't know the acceleration. So our job here is to come up with an expression for the acceleration. That's probably going to involve us using our net torque equation. So it's at this moment that we should probably determine what our object is. We could leave it in terms of I if you'd like, or we can do this in terms of a disk, a hollow ball, or a solid ball. You pick. Disk it is. So I equals 1/2 mr squared. We will indicate that that is the radius of the object. All good? So net torque equals I alpha. I don't think it's hard to see where the torque is. Can the weight cause a torque about the pivot point? Can't. And if I were you and you're taking notes, I would have this conversation. I'd put this conversation in your notes. Because if we shifted the pivot point to another location, you'll need to know why we would use some forces versus others. We won't use the weight as a torque because the torque arm between the center and where the weight is applied is 0. It's being applied at the center and our pivot point's at the center. So the weight can't apply a torque about the center. So that's why it's not applying a torque. Is the normal force applying a torque? It's applying its force a distance r away from the pivot point. Why isn't it applying a torque? It's the angle, yeah. The angle's 0 degrees, right? The normal force points right through the pivot point. So the angle would be 0 degrees, therefore it doesn't apply a torque. The only force that is acting in such a way that it can effectively cause a torque is the frictional force. The frictional force causes a torque because it's applying its force perpendicular to the torque arm, and it's applying that force a distance r away from the axis of rotation. So the torque from friction will be Rf. And I'm going to intentionally make this direction the positive direction, so out of the board. And that's going to make Rf equal to 1/2 mr squared times alpha. Now you'll remember, we're trying to figure out friction. Right now we have 3 relationships. Lots of unknowns here. Pretty sure there's 4 unknowns. A is an unknown, N is an unknown, friction is an unknown, and alpha is an unknown. Anything that we can do to reduce these unknowns? Go ahead.
Change alpha to A over R.
We can change alpha to A over R. By the definition of rolling, A has to equal alpha times R. Yeah. Doesn't really matter where we do this. but I think we eliminate more unknowns, or at least we eliminate more variables if we plug in for alpha here. So mg sine theta minus friction equals ma, and rf equals 1/2 mr squared a over r. So it seems to me that I could either solve for the acceleration or I could solve for the frictional force. I say we go ahead and do both. Let's reduce this by getting rid of all the r's, and we'll get friction equals 1/2 ma. I see substitution as our next step. So, right there. So mg sine theta minus 1/2 ma equals ma. Now, an object sliding down the ramp would have had an acceleration equal to would have had an acceleration equal to g sine theta. So for something that's just sliding down the ramp, that's its acceleration, assuming no friction. When we cancel out the m's here, and we solve this for a, we get that a is 2/3 g sine theta. This number, 2/3, is a product of how the moment of inertia factors in to the inertia of this object. That 2/3 exists because we added the 1/2 to the inertia for the the inertia of the ball by itself, just accelerating. That 1/2 created the 3/2, which created the 2/3 there. If this had been a ball, this would have been 2/3 or 2/5. You understand? That would have changed this number. So different objects will have a different acceleration because we will have a different value out front. Now, an object sliding without friction obviously slides the fastest. This one has to be sliding slower because there's friction acting. And friction acts, even though that friction is causing it to roll, it still acts against the direction of motion. What's really happening is energy is being taken away from the system to cause the object to roll. We'll be talking about the energy part of this next week. But in this case, the frictional force is being used to cause rotational motion instead of being caused to slow the object down. Now, if we want to find the size of that frictional force, that's probably the most straightforward way to do so. You guys see what I'm saying? Consider what you get when you do that. Friction is equal to 1/2 m times 2/3 g sine theta. M has to work itself into this because we're talking about a force now. And forces are always going to be connected to masses. So this becomes 1/3 mg sine theta. Remember a moment ago, normal force equaled mg cosine theta, right? This frictional force is the minimum required frictional force for this object to rotate. There might be more, but this is what's required to get it to rotate. Friction is on a sliding scale, though. For static friction, you can get more of this force. But this is what we require. Consider doing this. Putting this in for friction, and putting this in for the normal force. This tells you what the minimum coefficient has to be for the object to be able to roll. If you don't have enough coefficient of friction, then your object won't roll, it'll slide. But this is the amount of friction required for an object to roll. I bring this up only because it usually is very little. In this case, 1/3 mg sine theta. If this is a 30-degree ramp, then we're talking about a very little amount of friction required to make the object roll. But obviously, the steeper the ramp, the more friction will be required for it to roll. And I think you can imagine why that's true. You start making the ramp steeper and steeper and steeper, there's going to be more of a tendency for the object to slide because it has to rotate and accelerate faster to go down a steeper ramp. And that's what's going to cause more friction. So there's actually a limit to the angle you can use to cause something to rotate. And it says all of that right here. If we cancel out the mg, we can solve this for the angle. We get tan theta must be less than or equal to 3 times the coefficient of static friction. This is telling you that your static friction might not be sufficient, but it also is telling you that there are some angles you can't use. When you start to approach them, there won't be rotation. And obviously, if you remember how tangent works, what happens to tangent as you get closer to 90 degrees? Well, let's see. Sine of 90 is 1. Cosine of 90 is. So it becomes infinity at 90 degrees. That tells you that there is no coefficient that could be enough to get something to roll down a wall. It'll just fall instead. That's what that's saying. And you kind of know that. It might scrape against the wall, it might rotate a little bit, but it won't roll. That condition can't be met. There's no coefficient. It takes infinite coefficient of friction to get something to roll straight down a wall.